Yeah, so thanks everybody, and thanks especially to Anna for coordinating this and coming to the end of the year, doing this between everybody's marking, which is painful. But what I want to talk about is work that we've been doing over the last almost 10 years now, or even longer, looking at wave transformation through surf zones. And what I want to talk about here is specifically focusing on some of the unique aspects of how waves are transformed through reef surf zones. So this is work with a number of collaborators. I want to especially kind of point out Mark Buckley, who a lot of this work was during his PhD at UWA. He's now has a position at the USGS in St. Petersburg. So the motivation for this work is really trying to understand the various processes that drive coastal flooding and erosion along reef coastlines. And one of the things we often want to know is the extreme water levels that are generated, which is due to a number of processes and how they interact. So there's offshore processes like your storm surges, tides, long-term sea level variability. What I'm really going to be talking about is aspects of the wave-driven part of coastal flooding erosion, which is attributed to what we call wave run-up. And wave run-up is really a combination of a steady part, so a time averaged part, which is your wave setup, and then an unsteady part, which is these oscillations of the shore face, which are referred to as swash. And so the motivating question, in many ways this seems like an obvious question when you look at like photos like this, is how effective are reefs really at reducing coastal flooding and erosion? So we know shallow reefs are incredibly efficient at dissipating wave energy by depth limited breaking. And so when we look at pictures like this, we can see it looks like these shorelines are all completely protected from wave energy. But what I'm going to talk about is how it's often not a completely simple story, and we have to really understand these processes that occur when waves break and transform in the surf zone. So there's a lot of evidence where, in the literature now, where waves can actually cause an enhancement of coastal flooding when we get, particularly at really slowly varying motions like infragravity wave motions, very low frequency motions, and wave setup, which I'll talk about. And so there's cases like in Rober and Bricker where they see really exceptional damage when we excite these kind of low frequency waves on reefs, and a number of other studies have demonstrated that. I won't talk about the erosion. We're doing quite a bit of work looking at how reefs modify coastal erosion, but again, we really need to understand the details of how when waves break, that energy is not simply lost. It's going into other forms like generating, in this case, mean wave driven currents, analogous to rip currents, that can cause diverging currents along coastlines and actually cause enhancements of erosion. So in Western Australia, when we look at a lot of the reefs, we can find areas where these wave-driven currents behind reefs actually modify erosion substantially. And so really all of this is underpinned by understanding these energy transfers and these processes that occur in this narrow, really violent kind of energetic surf zone, where the energy that's feeding these processes is really driven by your incident wind wave energy. So waves, you see swell waves between typically 5 and 25 seconds. But when those waves break, that energy is not lost. It's not truly dissipated as heat. Only a very small fraction is that energy is going into like kinetic energy associated with driving mean currents, wave setup, which is the rise in the mean water level. Some of that sea swell wave energy is transmitted to the shoreline. And then also the excitement of these infragravity low frequency wave motions, which can have periods 25 seconds to several minutes. And so I'm really going to be focusing on a lot of these aspects. And one of the challenges and why these processes are very different in the surf zone of reefs is because of the sort of key physical properties of reef morphology. So waves, when they encounter reefs, reefs are typically forming out of deep water. So they often have, very steep slopes relative to mild sloping beaches where we have, 1:20 to 1:1 near vertical. That really affects how waves break. We have often diverse near-shore bathymetries which can play an important role in wave-driven flows, like when we have channels in reefs. I won't really talk much about that. But also reefs, the ecological communities in reefs create large roughness, and that plays, as I'll talk about, plays an important role as waves interact and currents interact with that large roughness. We get drag forces that dissipate energy and attenuate flows. And so these are properties that are quite different from beaches. And so what I'll be talking about is how some of the specific aspects of how waves break on reefs have a very important role in terms of understanding things like wave run-up along these coastlines. So when we think about waves breaking on beaches, obviously there's a diversity of beaches. We do get a wide range of different breaking processes, but looking at the limit where we have mild sloping beaches, we get spilling waves that dissipate their energy over wide surf zones that ultimately interact with the coastline. Reefs are different in the sense that we often have really plunging, kind of violent plunging waves into really shallow water. And the surf zones of reefs are also usually quite disconnected from the shoreline. This is a case of Ningaloo Reef in Western Australia, where the surf zone's in this case, about 2 kilometers offshore. So it's very different than cases like this, where the dissipation of waves are occurring all the way up to the shoreline. So just to highlight a couple of these aspects, so I talked about there's differences in how the waves break, but there's also key differences in the role of bottom roughness. So this is quite old work now, but really useful to illustrate the processes. That this is some field work that we did in a reef in Hawaii, where very simple measurements where we had wave gauges essentially across the reef. So offshore at site 1, which you can see here. So this is prior to the waves breaking, so we can see getting significant wave heights up to 2 meters. But when we looked at how much wave energy is dissipated across these reefs, some of it's dissipated by wave breaking, but a lot of it's actually dissipated by, and this isn't really a rough reef, this is an algal reef, but a lot of the energy is dissipated by this frictional dissipation. You can see that here is across the reef flat. At this point, there's no more wave breaking occurring, and we can see this gradual decay in waves all the way basically to 0 at the shoreline that's due to the bottom friction. So when we look at this specific reef, that on average, we estimate that about 60% of the incident wave energy is dissipated by bottom friction rather than wave breaking. And this is, for those who are familiar with how we kind of model and parameterize seabed interactions with wave friction factors, it's because the wave friction factors are typically 1 to 2 orders of magnitude greater than on typical sandy beaches. So what I want to really talk about in this presentation is hone in on some of the experimental measurements we've done, looking at some of the fine details of wave transformation across reefs, focusing on the cross-shore dynamics. So I'll look at some of the the aspects of how these different contributions to run-up vary on reefs, how they contribute to wave run-up and the influence of bottom roughness. And then what I want to sort of just finish on is briefly talking about it's really an active area of research, which is looking at really highly resolved numerical simulations of these surf zone processes using new CFD modeling approaches and some of the new insight that those tools are providing. Okay, so first thing I want to just talk about, and this is very typical of reefs, and so there's a number of field studies that have looked at wave transformation across fringing reef profiles like this, and this is quite typical where offshore we have our wind waves, our sea swell waves, again, which are, if we look at the energy, wave energy within the band that's 5 to 25 seconds, that's your sea swell waves. Clearly, the incident waves are mostly all in that sea swell band. There's some Low frequency infragravity wave motion, those are waves between 25 and 250 seconds. That's, as I'll talk about, that's due to bound wave energy that's associated with wave groups. But when we see the sea swell wave, so this is the white areas here, this is the waves we see, the sea swell wave energy breaking. We get a dramatic decrease in the swell wave heights, and we get an increase actually in the infragravity wave height. So right out of the surf zone, there's more or sort of balance between swell and infragravity wave motions. As we move further across the reef, and there's reasons for this, which I won't talk about, but shorter period waves are more efficient at being dissipated by bottom friction. So we see the swell waves decaying to very small values by the time we reach the shoreline, and we see the infragravity waves don't decay. So we get this dominance of infragravity waves, which are really driving water level variations and run up at the coastline. So that's one interesting aspect. The other aspect is how wave setup generation occurs on reefs. And so what's commonly observed is we can get really large increases of mean water levels on reefs, depending on the depth and the slope of those reefs. This is old work by Gourlay, which summarized sort of experimental measurements, which if you look at the y-axis, this is the mean water level wave setup on the reef divided by the offshore wave height. And this is the little h is the depth of the reef divided by the offshore wave height. And what we can see is that we get a lot of, particularly for shallow reefs with steep slopes, we get a lot of times where the actual mean water level, the whole reef water level can be raised up by about a half of the offshore wave height. And this is very different than typical beaches where it's more like order 10%. And so what I'm going to do is I'm going to talk quite a bit about why this is the case. And it really comes down to looking at our mean momentum balances, which are used to explain how we get, so this is a setup generation here, which is our wave setup gradients. So this is our pressure gradient term. We'll talk about radiation stress gradients, which is essentially looking at how waves are attenuated and the wave forces that are generated as waves break and decay across the reef. And we also get this mean bottom stress term, which I'll talk about. So if we look at places like Ningaloo, if we measure setup, so what's shown here is some measurements of wave setup versus offshore significant wave height. We can see in this case, 30% of the offshore wave height is going into wave setup. So the whole lagoon is essentially being raised by about a half a meter, just only for 2 meter high waves. So it's quite remarkable. Okay, so there's a lot we can do with field measurements, but one of the things we did, and this was work as part of Mark Buckley's PhD, where we really wanted to get at really detailed observations through the surf zone of these reefs and really understand important questions like what's the role of the steepness, the water depth in terms of driving, the transformation of waves, the generation of wave setup, and then also what's the role of bottom roughness on these processes. So we did quite extensive experiments in a 55-meter long wave flume, and we essentially built a reef where we scaled that down by 1/36 scaling, kind of roughly similar to as a prototype for something like Ningaloo Reef. And one of the advantages when you do these in physical model testing is we can get really detailed measurements through the surf zone. So we had 16 wave and water level measurements through the surf zone. 18 wave gauges, and then also velocity measurements. And we could run this over a range of different offshore wave conditions and mean water level relative to the reef flat depth. And also with this, which I'll talk about, we had a run-up gauge where we can measure wave run-up due to all these different conditions. And one of the nice things about this experiment is we could also look at the effect of bottom roughness. And so obviously, natural reefs are extremely complex in terms of the roughness. But as I mentioned before, we sort of know the bulk characteristics of how wave energy is dissipated on these reefs. We understand like what the typical wave friction factors are. And so we designed roughness that's very simple, but we designed it so it would have a similar bulk frictional dissipation characteristic to like a typical value on natural reef. So we built this reef with these concrete cubes and arrays, which then provide a way to look at the effect of going from a smooth reef to a rough reef. I won't really talk about all the fine details because I'm going to get more into in these results later, but just want to show the type of information that we get. So what is shown here is one case, one wave case and water level case where we compare the smooth cases and the rough cases. We can get detailed measurements at all of those locations, which I mentioned. And we can decompose the wave heights into our sea swell waves. So in the field, if we translated this into field time scales, this would be 25 seconds or less. I'm going to define this high frequency infragravity wave band, which is between 25 and 100 seconds. And this is going to be important. We're going to see these low frequency infragravity waves, which are in the field, this would be your 2 minutes or tens of minutes even. So these are really low frequency kind of satiating modes that occur on these reefs. And what we can do is look at the differences, for example, between the smooth and the rough case, where we can see, for example, if we have the rough case, you can see there's very slight differences in terms of the sea swell waves. Differences in terms of the high infragravity wave band. You can see quite big differences if we compare the black and the red squares in this low frequency infragravity wave. And we can look at the differences in the setup. So I want to talk about, so those are the type of measurements we get, and I want to talk about some of the main points that we see when we look at these results in detail. So the first thing I want to do is then translate this and what does this mean for wave run-up? So this is again a busy figure. So if you want to look at this paper, JGR paper in 2018, but one of the things that we were able to do in this work is look at, for all these different cases, what are the factors that contribute to run-up, how that varies with bottom roughness. And what is shown here, so this is measurements with the run-up gauge, where we can measure the total run-up, which is our 2% exceedance run-up. And this is for one offshore water level, and we just increase the wave height, and we look at the run-up response at the shoreline. And we can see, not surprisingly, we get a more or less linear increase in wave run-up with wave height, this R2%. We get slightly less run-up if we have the roughness there, so it is reducing, in this case, reducing what you would expect with wave-driven flooding. But one of the important things, and why I want to show this slide, is we can then decompose the total run-up that we see into the factors that contribute to that. And this is like decomposing the sea swell wave, the high infragravity, the low, and the wave setup part to run up by the superposition. And really, the main thing is to focus on this right set of panels, which is essentially showing the fraction of the total run-up that's explained by each of these components. So for example, when we see a value of 0.2 for the sea swell, it's saying that up to about 20% of the wave run-up we see in all these cases is due to the sea swell. If we look, however, we see the sea swell and these high infragravity waves tend to be contributing less, 0 to 20%. It's really these low frequency motions, these low infragravity waves, that are contributing between 20 and 40% to run up, independent of whether we have smooth and rough cases. And also wave setup is, in many cases up to 30 to 50%. So it's really these processes on these reefs that are dominant, and they're actually also perhaps the most difficult to predict. So I'm really going to spend time in a couple slides just talking about these processes in more detail. So the first thing I want to discuss is how wave setup is generated, and why do we see such large wave setup values over reefs. And so the value of these experimental measurements is we have really detailed observations through the surf zone. And so we can calculate from the water level measurements, we can get an estimate of radiation stresses, which radiation stresses are really a representation of the momentum, the excess momentum flux of waves, and gradients and changes in those radiation stresses are providing wave forces that drive setup. And so if we have a smooth case here, if I go back to here, we don't have our mean bottom stresses are 0. So we have this balance between wave setup gradient term, a pressure gradient term, and our radiation stress gradients. And we can measure, based on the water level measurements, we can look at what our radiation stress measurements tell us. And if we integrate that direct measurement based on the water levels, we get, so the observed setup are these dots. If we take the measured radiation stresses, we get this black hash line here. And we find that we can't explain why we get these large wave setup values. And so what we've found through this work is it really gets into the details of how wave forces are generated in the surf zone, where radiation stresses, and I'll talk more about this later, is they have a part that's related to the potential energy, that's related to the water level variance, and a kinetic energy, which is like your turbulent velocities and so on. And what we have when waves break is we get a decay in the potential energy, but we get what's called a roller that's established that generates all this turbulent kinetic energy. And that pushes the wave forces into shallower water. So this is this concept of a roller, why people use roller models sometimes in predicting surf zone processes. And it essentially pushes the radiation stress gradients shoreward. And one of the things we show is when, for the same value of a radiation stress gradient, if that occurs in shallower water when H is smaller, we get a larger setup response. So for the same decay, so you can see the slopes of that radiation stress are similar, but because they're occurring in shallower water on top of the reef, we get a significant increase in wave setup. And so what we've done through all this work is we can actually explain why we get these large setup values, and we can reproduce both our set down and setup is if we include this effect of a wave roller, which is, you can see if we collapse on the one-to-one line, if we don't include this, we significantly underpredict wave setup. Now for the influence of roughness, and again, it's quite subtle and it's not necessarily obvious, is when we include bottom roughness on a reef and we look at the wave averaged, the mean momentum balances, we have an extra term, and this is the time averaged bottom stress that occurs as the waves and the flows interact with that bottom roughness. And so what we can do in this case is we can look at, again, measure the radiation stresses across the reef, and because as the waves interact with the bottom roughness, we get dissipation. So you can see the rough cases, the radiation stresses are actually decreasing. So you might expect from that we might get more setup. But if you look at comparing the smooth and the rough cases, we get, so the red and black, we get the same amount of setup. And so what essentially happens in this case is we get, with the roughness, we get a time average bottom stress that's exerted on the seabed, which actually contributes to increasing roughness. So we get this sort of counteracting processes where we get the same setup occurring between, independent of whether we have a smooth or a rough bed. And so really accounting for these details in terms of these mean bottom stresses is also critical. So the last thing about when we talk about some of these key wave transformation processes is understanding the role of these low frequency waves. And so many of you are familiar when we think about waves, wind waves offshore, we have waves of different frequency interacting in the parts of the spectrum where we have similar frequencies. Those interact and cause this kind of beating pattern that gives us our wave groups. And so when these wave groups, essentially sets of waves, interact with these reefs, they generate forcing at the time scale of these wave groups, which then interact with the reef morphology, the bathymetry profile in the bottom roughness. And so one of the things which I talked about is we get a lot of infragravity wave motion, and a lot of this low frequency infragravity wave motion generated on these reefs. This is, I won't talk about these, but these are swash phase resolving wave model simulations of these cases, but it's good to illustrate what's actually happening, where we can get the total water level signal out of swash, and we can decompose that into those same frequency bands. So we can see when these waves approach the reef, they break and the sea swell waves are dissipated. This is your high part of the infragravity waves. You can see relatively small, but you can see these really slow, I mean, this is a good way to visualize what's actually happening. These are really slow, low frequency, often called VLF or very low frequency motions that are essentially satiating across the reef, where we can get a mode 0, which you can see is always highest at the shoreline, and a mode 1, which has a node in the middle. And so what we can do with this is we can look at, essentially, as we have these groups of waves breaking, that energy is essentially going in and pumping energy into these natural frequencies where we get these very low frequency motions on a reef. And so if we look at sort of the envelope of those motions, we can see we get a node, so a minimum in displacement near the crest, and then one antinode at the shoreline. And then this is the mode 1, where we get a node here. And so it's basically these low frequency motions that are being excited and are contributing to wave runoff. So on a lot of these reef coastlines, again, we see wave setup being important, and also these low frequency wave motions. What I want to finish on, this will just take probably 5 minutes or so, is talk about what current focus has been on, is really trying to really hone in on some of the fine details of what's happening in surf zone. So we've shown a lot of processes that we know are important, but even with physical model testing in labs, it's, for example, impossible to measure all the fine details of velocities in the plunging parts of waves when they're breaking. And so was lucky to be on sabbatical a couple of years ago and had time to spend quite a bit of time looking at new modeling approaches for looking at some of these surf zone processes. And I'll talk about those. And one of the advantages with these modeling approaches I'll talk about is they're really effective and efficiently effective at reproducing some of the hydrodynamic processes in the surf zone through plunging waves, and can deal with quite complicated geometries and so on. So this is approach it's a computational fluid dynamics approach referred to as smooth particle hydrodynamics. It's fundamentally, it's not different than any traditional CFD modeling approach, but the main advantage is it's meshless. So it's still solving the Navier-Stokes equation, but instead of having a fixed grid like we're generally used to with models, we have essentially nodes that are based on defining parcels of water that are defined by mass, and defining a kernel region where we looking at things like gradients and so on by looking at how this occurs over these neighboring particles. So the particles travel with the fluid motion, and their properties change with time. And one of the advantages is these are highly efficient in terms of running on graphical processor units, by the fact that we can treat these different parcels of water essentially as independent over most of the computation cycle. So we can really run very high resolution simulations, which I'll show. And so one of the first things we did is, there's a lot of literature on SPH models. They've shown promise. A lot of them are really kind of coastal engineering focus, where they're looking at the ability of these models to predict like bulk wave heights, run up, loads on coastal structures and so on. But one of the things we wanted to do in this study is really get into the fine details and benchmark these against other types of CFD type models like OpenFOAM. And so we did a detailed study where we looked at two cases, a plain beach case, where this is a really widely used study in Ting and Kirby, which is looking at spilling and plunging waves on a plain beach, and looking at things like the nonlinear wave energy transformation, surf zone turbulence setup, mean currents, and starting with simple kind of regular waves, and then also looking at this reef case. So what you can see here is just shows, so this is really highly resolved simulations of wave breaking. This was sort of the first test case we did looking at that Ting and Kirby plain beach, and so we can see we get like a spilling waves occurring here and then plunging waves as we increase the wave period. So this is really resolving millimeter scale hydrodynamic processes within these experiments. Kind of skip through this quickly. So if you're interested in looking at that paper, we've done a lot of validation and pulling apart. So this is just showing like comparison with the wave envelope, the crest and trough locations between the experiments and the models and wave setup. One of the interesting aspects, if we look at undertow, so even CFD models tend to, like OpenFOAM, mesh-based CFD models tend to still struggle with things like undertow and getting the mass fluxes right. We found that this approach worked quite well at reproducing the undertow profiles in these experiments. And so this was the foundation for what my current focus has been on, is now tying this together and bringing this to simulating these Buckley reef experiments, which I was talking about. And so one of the challenges with that is, even though we're using GPUs and it's quite efficient, when we think about trying to simulate like a 50-meter long wave flume with millimeter scale resolution, and then also we need to run for very long to resolve these really slowly varying, very low frequency waves. That's a huge bottleneck. And so with a group, Corrado Altamar in Barcelona, we've been working on new approaches and different approaches than even the current case to couple this dual-S physics model to swash, where we essentially run swash over the full domain, and then we focus just on the fore reef and the reef flat with dual-S physics. And so now we can actually run these highly resolved simulations for the very long periods of time, getting thousands of waves and also getting irregular wave conditions. Probably just blast through this because I'm late, but what we can see is we had in those experiments, we had detailed georeferenced imagery. And so we can see at a location just x = 0 is the reef crest, and this is slightly offshore. The red lines are the dual-S physics SPH simulations. We can see we capture these kind of complex wave shape evolution across the reef. And you can look at one wave cycle where we can see the waves breaking, overturning, this kind of splash up, it's more or less capturing, and so on. Again, looking at some of the bulk parameter comparisons where we can look at, as I talked about before, for this experiment, the sea swell wave, the high infragravity waves, the low infragravity waves, so you can see the evidence of this node that's here, this spectral wave period, so you can see the increase in the long period spectral bandwidth and wave setup. And also similarly looking at the spectral evolution. So we can really see the black is the observations, red are the predicted. We can see offshore, so negative values, x = 0 is where the reef crest is. You can see we get, this is a sea swell wave peak. We start to get these super harmonics being excited, but then you can see right when we get to the surf zone, we get all this low frequency to the point where it's all really low frequency infragravity wave motions at the shoreline that are reproduced by the model. might just skip over this, but this is really just showing that we can reproduce the nodes and the antinodes of those low frequency waves. And with this, we can get pretty interesting results. And I think a lot of this confirms a lot of suspicions we had when thinking about hydrodynamic processes on the fore reef and where waves are breaking on reefs. So maybe skip over this, but one of the interesting things is if we look at the mean flow patterns that are generated at the reef crest as these waves break, we can see the blue are negative offshore velocities. So this is your undertow, but we can see how that evolves and we get sort of this entrainment. But we get these really strong flows down the fore reef slope, and I think that's quite consistent with what people think, even like spur and groove kind of formations that move sediment offshore. And we get these interesting kind of eddies that form on the fore reef. So with this kind of information, we get a lot of information that we're just starting to look at. The last slide I'll show is connecting it to the first part, where with this now we can directly get at all the aspects of mean momentum balances by we have all the information to directly calculate radiation stresses, which have a part that's related to the kinetic energy and a part that's related to the potential energy. And if we directly calculate the radiation stresses coming out of this highly resolved model, we get the red line here. So you can see it's higher and it's also pushed forward than if we take these observations and we use linear wave theory. And so this is the effect of the roller. So we're capturing that, and we're capturing how if we directly include all of the parts to the radiation stress, we can reproduce a setup profile similar to what I showed with the experimental observations. If we just use linear wave theory, we can't, we underpredict setup. So we're starting to look at all this, and it's really sort of exciting that we can use this now to really have all of the information we need to look at some of these surf zone processes. Skip over this. This is looking at some of the vertical parts of the momentum balances, which I won't talk about. So just to conclude, one of the things we've done is really shown how we can improve predictions of wave setup and understand why it's underpredicted on steep slope using just simple kind of radiation stress theory based on linear wave theory, and the differences between what occurs on mild sloping beaches, the importance of including this wave roller effect, which is really describing how when waves break, the height initially drops, but the energy is not lost. It's going into driving a lot of kinetic energy, a lot of vorticity and so on that occurs, and that's delaying the wave forces and pushing those shoreward. Talked about how the bottom roughness has a substantial effect on wave setup. And if you look at this paper, there's quite interesting details. I haven't really talked about it, but really how we describe the velocities interacting with the bed is very important. It really depends on accurately getting the wave shape right. And this new tool, this SPH approach, is providing sort of new insight really into understanding some of these surf zone hydrodynamics. And it's really well suited to these cases where we really have these plunging waves where we don't have to rely on meshes. And so most of this work is included in these papers here. So if you want to have a look at more details, they're included there. All right, thanks.
Thanks a lot, Ryan. Excellent talk. We've got about 9 minutes left for discussion. So there are a few ways you can do it. You can write a question in the chat, or you can raise your hand, or you can just jump in. I see Giovanni. No, that's an applause by Giovanni. So if anyone has any questions.
I thought he'd have a negative comment about SPH models, but